So for number 1 here, the best test for determining whether an unknown compound is ionic or molecular would be to test what? Conductivity. Okay? The conductivity test, or conductivity of the solution, okay, something about conductivity, that is the test that unequivocally tells you yes or no. Is it ionic or molecular? Okay? Number 2, if something has a pH of less than 7, what is it? An acid. Okay, you have a sample of an unknown compound and you add it to water and the solution turns blue. What metal does it contain? Copper. Alright, for number 4 here, we got to give the name of this compound. Ca stands for calcium, NO3 is nitrate, so this stuff is calcium nitrate. If there are any capitals in their name, it is wrong. Okay, we must not have any capital letters. As we've said several times, there are no capitals. Alright, I'll be a nice guy. Half off if they have capitals today. Okay, if they have any capitals, it's half off. Alright, number 5. I've got silicone and oxygen together, so this is a molecular compound, which means I need prefixes. So I have disilicone trioxide. They don't have to have the hyphen, okay, as long as they have disilicone trioxide. Number 6, I've got lead and oxygen, which is an ionic compound, but lead has more than one possible charge. It can be a 2 or a 4. So what I have to figure out is, which one is it? Well, every oxygen is -2. 2 times -2 is -4. There's only one lead here, so it has to be +4. So this is lead, Roman numeral 4, oxide. If they don't have the Roman numeral, it's wrong. No half marks on that one. It's just wrong if they don't have the Roman numeral or they have the wrong Roman numeral. Okay, number 7, we've got potassium and phosphorus, an ionic compound, so this is simply potassium phosphide. Questions on those 4? Okay. For our last 4 here, we got to give the formulas. Sulfur dichloride. So this is a molecular compound. The prefixes tell me how much of everything there is. There's 1 sulfur and there's 2 chlorines. Okay, they either have that formula right or they don't. There's no half marks on that. Okay, number 9, magnesium phosphide. Okay, it's an ionic compound, so magnesium is 2+, phosphide is -3, drop and swap. You got Mg3P2. Alright, for number 10, we have cobalt-2 nitride. What does the Roman numeral tell me? Right, cobalt has a charge of 2 in this compound. So CO is 2+, nitride is -3, drop and swap, CO3N2. And there's your formula. And lastly, number 11, sodium carbonate. The formula for sodium is Na. Because that's a metal, this is an ionic compound, so I'll have to drop and swap again. Okay, it's +1. Carbonate is a polyatomic ion, CO3, and it has a charge of -2. So you should have Na2CO3 for the formula there. Alright, the whole thing is out of 11, so give them a mark out of 11. Write it at the top of the page. And then give it back to them, and then I want them in the box, period 4 box, right here, please. So what we're going over today should be a little bit helpful in your lab tomorrow, at least in terms of the solubility test, okay, that you will be running. We're also going to talk about some of the strange properties that water has, why it does some of the things it does, okay, and then obviously, if we have a little bit of time left after that, you'll have some more time to work with your group on your procedure and other pre-lab activities. Those must be done for tomorrow. If your pre-lab activities, that means problem, design, hypothesis, procedure, okay, and your chart are not ready to go at the beginning of class tomorrow, you will be sitting in this classroom until they are, okay, while the rest of us do the lab. So please make sure you have all of that stuff ready for the start of class tomorrow. Okay, what we're doing today, learn the terminology related to solubility. So there's some vocabulary here, so you'll want to do a little highlighting or starring or whatever. Okay, understand what is meant by the term polar molecule. That's one of the things that will be about water in particular. Okay, and understand that because it is a polar molecule, water has many important and unique properties that make life on Earth possible. Okay, so being a polar molecule means a lot, okay, and we'll actually come back to that in a couple of other units, okay, as well. Okay, obviously some things dissolve more easily than others, okay. The degree to which something dissolves in something else is called solubility. All right, it doesn't have to be water, okay, but most often it is. I mean, that's what we dissolve most things in. All right, is everything soluble in water? No. Okay. We have a lot of things that we purposefully have designed so that they do not dissolve in water. Anyone think of any? What are some things that we have purposefully designed not to dissolve in water? Okay, some types of metals, yep. Okay, again, type of metal, yep. What about paint? When you put paint on a wall or paint on a house or paint on a car, is that supposed to be protecting it from water and other things? Yeah, okay. I mean, there are some water-based paints, okay, like latex paints are water-based, which means before they dry or shortly after they dry, you can still wash them off with soap and water, okay? But your oil-based paints, your stains and things like that, are designed specifically to repel water. Right? If you've ever seen what a freshly stained deck looks like on the first rain it experiences, the water kind of beads on it, okay, and runs off. Same as on a car, if you've just waxed it, okay, the water beads and runs off, doesn't penetrate through into the paint or into the other parts of the car. Dyes, yep, some dyes we don't want to be soluble in water. If you want your shirt to stay red or black or whatever, you don't want it to fade. Okay? If you accidentally put bleach in there, bleach will take care of that for you. Okay, it will make it fade right away. All right, on most dyes and things like that. Okay, so some things, yes, we want them to dissolve in water. Okay, water doesn't dissolve everything easily. Okay, things that are oily tend to not dissolve in water. Sometimes those things need a little help. Right? And so we might put in things like soap. Okay? Soap helps to break up or emulsify oily substances and make them more soluble than they would normally be. All right? You guys have probably all seen, if you've ever done the dishes, okay? You put an oily pan in the water, nothing really happens. You put a little soap in there, and pretty soon stuff starts to happen. Okay? Stuff starts to get cleaned off a lot more easily. All right, so again, that's what solubility is, the degree to which something will dissolve in something else. Okay, so if we're looking at this picture here on the left, okay, obviously that material, okay, or that stuff there has completely dissolved. We only see one visible part. Whereas this stuff on the right, okay, there's more than one visible part. Okay, there's this part here at the bottom, and then there's this part here at the top that is clearly not dissolved. Okay. And those form different types of solutions and mixtures. All right. If a substance doesn't dissolve or is not soluble, we tend to call it a precipitate. Okay? The reason for that is solids that are produced in a reaction, okay, so sometimes you can add two things that are soluble together and you'll get a solid form out of them. All right? And it tends to fall out of the solution and down towards the bottom of the container, just like snow or rain falls out of the sky. Anything that falls out of something else tends to be called a precipitate. Okay, precipitation, precipitate. All right, Grayson. Thanks. All right, so terminology here. Solution. A solution is any mixture containing a solute dissolved in a solvent. We'll talk about what solutes and solvents are in a minute. Okay, it is also known as a homogeneous mixture, okay, or homogeneous mixture, however you want to pronounce it. Either way is fine with me. All right, so any mixture that contains a solute dissolved in a solvent. Okay, solvents we typically apply that term to like cleaners and things like that, like like CLR or Tilex or things like that, Mr. Clean, right? Those tend to be what we call cleaning solvents, because what do? They help dissolve the crud that tends to form in your bathtub or toilet and whatever. Okay, they tend to make that dissolve more easily. Anything that dissolves something else is a solvent. Anything that dissolves in something is a solute. All right, so salt in water, salt is a solute. All right. Okay, now if you have a mixture that has one visible part, you have a homogeneous or homogeneous mixture or a solution. Okay, if you have this, a mixture with more than one visible part, you have a heterogeneous or mechanical mixture. It is not a solution. Okay, everybody with me there? Okay, I will expect you to be able to use the terms homogeneous and heterogeneous. Okay, I will say this so that you will never forget it. What does the term homo mean? Same. Yeah, or one. All right, a homosexual couple has only one gender in it. Everybody follow me? Okay, homosexual means one sex. Heterosexual is two. Everybody follow? That's what the term is. Now you'll never forget. Okay? So a heterogeneous mixture has two or more visible parts. A homogeneous mixture has one visible part. All right? If you have homogenized milk, all milk is homogenized. It's just only one percentage of fat is called homogenized. But okay, it's called homogenized because it stays as one part in your fridge. Anyone ever seen what happens to milk right out of the cow? It separates. Okay, there's a pasteurization process that goes on that keeps it homogenized so that it is one visible part. Okay, peanut butter. Most types of peanut butter are also pasteurized so that they stay homogeneous. All right. If not, the oil, the peanut oil, will rise to the top, and the rest of the stuff will go to the bottom, and you have to stir it every time. All right. If you get like organic or special other kinds of kind of nut butters like almond butter and things like that, they tend to separate. All right. They don't tend to stay together. All right. So does everyone follow the difference there? Okay. So heterogeneous mixtures. Okay. Things that oil and water, iron filings in sand. Okay. Chicken noodle soup. All right. Heterogeneous mixture's got more than one part. It's got noodles and chicken and whatever else. Okay. Even then, the noodles don't dissolve. They might be made into smaller parts, but they still don't dissolve. Okay, follow me there? All right. Now, if you just buy the broth would obviously be a homogeneous solution. All right. So again, solute here. Solute is the substance that is being dissolved. If I pour salt into water, salt is the solute. It is the thing that's going to get dissolved. Sugar in your coffee, okay? That's the solute. Sugar is the solute. Coffee is the solvent, right? Whatever does the dissolving is the solvent. So if you've ever, let's say, painted, okay, with oil-based paint or something like that, or stain, if you want to clean that off of your hands, it doesn't come off with soap and water. What do you have to use instead? Gasoline, Varsol, paint thinner, okay, any of those type of things, because they are solvents that will dissolve things like paint. Okay, that's why you don't want to pour gas on. Well, you don't want to pour gas on very many things because it's quite flammable, obviously. Okay, but it will also dissolve paint, take paint off of surfaces and things like that. Okay, mosquito repellent will do that too if you're not careful. Okay, if you get strong mosquito repellent, it often has a warning: do not use on painted surfaces. Okay, because it'll start dissolving the paint. Okay, and take it right off. All right, is that making sense to everybody? Solute and solvent, okay, simple definitions, but okay, these are terms you're going to have to be able to use. All right, so a precipitate is any solid that's produced in a reaction and as a result will not dissolve in the solution. Okay, and I'll show you that here in a second. Okay, and again, here's the definition of solubility. Okay, it's the degree to which a substance will dissolve in another substance. Okay, how much solute can go into something before it stops dissolving. Okay, when it stops dissolving, it is said to be saturated. Okay. When I make Kool-Aid, I make a saturated solution. I don't know how you guys make Kool-Aid, but I actually make it with warm water. Okay? That way I can get more sugar to dissolve in it. Okay? Because solubility is affected by temperature, and more sugar will dissolve in warm water than it will in cold. All right? So I mix it up, get all the sugar to dissolve, I put it in the fridge, and then when I take it out and it's cold, there's this thin layer of sugar on the bottom of the container. That's the sign that it's good. Okay? Because it is a saturated solution of sugar and whatever awful things are in Kool-Aid. Okay? Everyone follow me there? You guys all made Kool-Aid before, right? Okay. Now, here's something gross for you. How many of you like Twinkies? Okay? You won't like Twinkies after this. Okay? The original Twinkie was actually cake. Okay, and cake, real cake, contains things like eggs and oil, okay, and flour and stuff like that. Stuff that unfortunately spoils quickly when placed on a shelf. So the manufacturers of Twinkies found a way to replace these natural ingredients with artificial ones. Okay, so they started replacing eggs with certain things. They started replacing the oils and the milk and whatever else with artificial replacements. There was one problem they had, though. The Twinkies didn't look right because they no longer had eggs in them. Eggs is what is supposed to give the yellow color to Twinkies. Because they no longer contain real eggs, they have to have yellow dye number 5 added to them. Okay? Yellow dye number 5 is highly soluble in water. It is also a known carcinogen. That means it causes cancer. It's actually banned in most of the European countries. Okay? However, we want yellow Twinkies. So it's okay here, for whatever reason. Okay? But if you don't put yellow dye number 5 in a modern Twinkie, it looks like drywall paste. It's gray and unappetizing looking. All right? It has to have this other stuff added to it. Now, because there's no actual oils, no actual eggs, no actual milk in a modern Twinkie, a modern Twinkie will dissolve in water. Okay? The original Twinkie wouldn't. It would get swollen, but it wouldn't dissolve because it had oils and eggs and stuff in it that were not soluble in water. But the modern Twinkie turns into that gooey paste, okay, when put into water. Yes. So if you ever broke your jaw and had your jaw wired shut and real had a hankering for a Twinkie, okay, you could just put it in a glass of water and wait about an hour, and you'd be able to drink it. If you couldn't wait an hour, throw it in water in a blender, and you got a Twinkie shake. Okay? But it is soluble in water now, okay, including the filling. Okay? Even the filling is soluble in water. It didn't used to be either. The original filling contained oils and things like that that would not dissolve. All right, so yeah, modern science does weird stuff. All right, so to have a look at these quick videos here. All right, so has everyone got those terms down? Okay, saturated, okay, solubility, precipitate, okay, again, important things to know, right? They could be part of questions later. Now, on your periodic table, you have this. So if you can take out your periodic table, okay, and on the back side of the periodic table, you'll see this chart. This is a solubility chart. It tells you what combination of elements will produce soluble materials or insoluble materials. If something is insoluble, obviously it doesn't dissolve in water. All right? So here's how we use this. If I was to say, let's say given a particular compound, let's say I was told, find out whether this stuff would dissolve in water or not. Okay? First off, what's that stuff called? Sodium hydroxide. Right? So this is what I do. I look on the top row and I find the negatively charged part of my ionic compound. Okay? And I see that here's OH. And I see that Na is here in the first row. And it says here on the chart that anything in the first row is very soluble. All right? So that means that sodium hydroxide is very soluble in water. Everyone follow me on that? Okay? Let's have you try this one. Lead 2 iodide. All All right, so we look up iodine on here. Iodine is right here. It says it is soluble with most things, but it is not soluble with copper, silver, mercury of either charge, okay, or lead too. Okay, so is that stuff soluble or not? It is not soluble. That stuff would be a precipitate. In fact, it is a bright yellow precipitate. Okay, everybody follow me there? All right, so that's kind of what we're looking at, okay, in terms of being able to use this solubility chart. So here's what I'm going to do. I'm going to write a few compounds down here. You use the chart to figure out whether they're soluble or not, and then we'll go through them together. All right, so let's just quickly go over these here. So our first one here is strontium chloride. Okay, so we go up top, we look up chloride. Okay, chloride is right here. It says soluble with most things, but not with these guys down here. But strontium is not amongst those. Okay, so this compound is soluble. Okay, lead 2 nitrate. All right, so we find nitrate. Nitrate's right here. Soluble with most things, but not with these big complex things down below. Most nitrates are soluble. Just about everything is soluble with nitrate. Yeah, we'll say anything that's down here, they say slightly soluble, but essentially that means, yeah, some tiny part of it dissolves, but the majority of it sits on the bottom. Okay. All right, sodium sulfide. So we go up top, we find sulfide. Sulfide is right here, and you can see that sodium is in that top row. Okay, so that is one that is soluble. Okay, silver sulfate. So we find sulfate right here, soluble with most things, but silver is listed down in the insoluble row. All right, so that stuff, okay, not soluble. And then we have potassium iodide. So iodine is right here, soluble with most things, but not, again, with these 5 things down here. Potassium's not among those, so that one is soluble. And then we've got copper 1 chloride. All right, so we look up chlorine here. Again, soluble with most, but copper 1 plus is in the insoluble row, so this is not soluble. Everybody with me there? Okay. Earlier, when we were talking about what happens in a molecular compound, in terms of what happens with the electrons, we talked about how molecular compounds share their electrons with each other. It isn't a trading or swapping of electrons like in an ionic compound. And we said that that makes molecular compounds quite a bit more stable. They hold on to each other a lot more tightly. Well, water is a molecular compound, but it is also what we call a polar molecule. And in a polar molecule, yes, we're sharing the electrons, but that sharing isn't equal. All right? It's like if you get a pizza, you and a friend, but one of you eats 8 pieces and the other eats 2. Sure, you shared it, okay? But did you get as much as he did? No. All right? Well, that's kind of what a polar molecule is like. A polar molecule, they're sharing the electrons, but they're more often at one end of the atom, one end of the molecule than at the other. All right? So if we're looking at water here in this picture, okay, we can see that oxygen, okay, it's got 8 protons, it's got 8 of its own electrons. Hydrogen's up here, it's got 1 proton and 1 electron. Okay? But oxygen is very electronegative. All right? And electronegative means that it likes electrons and it can hold them very tightly. So when it bonds with hydrogen atoms, the electrons from the hydrogen atoms tend to stay down in this area as opposed to up here. All right? So their orbits around, orbits for lack of a better word, orbits around the nucleus of the hydrogen atom become abbreviated, and they don't spend very much time out here. They spend the majority of their time down in here. In fact, they may not actually orbit anymore. They may actually stay in the cloud closest to the oxygen atom. Okay, everybody with me there? Now that may not seem all that important, but it has a major effect on the behavior of water. If all of the electrons are now down closer to the oxygen atom, this end of the atom becomes negative, and this end of the molecule, becomes negative, and this end becomes positive. So you got these 2 positive charges kind of sticking out from the top of the Mickey Mouse shape, okay? And you've got these negative charges down below on the bottom of the oxygen atom. What do opposites do? they attract. So you never see one water molecule hanging around by itself. There's always other ones around. And they can become attracted to each other as long as they're oriented the right way. So if another water molecule comes around, the negative end of it will be attracted to the positive end of the other one. And they'll form a weak bond called a hydrogen bond. Okay, so this here is a hydrogen bond. Okay, when two water molecules or more bond together, they stick. Okay, where have you ever seen evidence of this happening? Anybody ever filled a glass more than full? You ever seen that layer that forms, that surface tension that happens? Okay, surface tension is the result of hydrogen bonding between the polar water molecules. Okay, they actually bond to each other and they'll hold each other there. Is it very strong? No. Okay, it's not like you can fill it like way over the top, but you can fill it a little bit over the top. Now, if you come along and touch it, what happens? It breaks. Yeah. Hydrogen bonds aren't really strong. They're just strong enough to do kind of weird stuff. All right. So they cause this surface tension to happen. Okay. They also have that. They also have the ability to make the condensation that's on the outside of a glass stick to it and not necessarily roll down. You ever notice how small droplets of water will stick on the side of the glass, but they won't slide down it until they get to a certain size, and then they're just too heavy to hold there? Okay, that's the result of the water molecule actually bonding to the glass. Okay, the glass has a negative kind of charge on it, and it's attracted to the positive charge of the water. Okay, and they'll bond to each other. Okay, temporarily with a hydrogen bond. Everybody with me there? Okay, it's also what allows the Jesus lizard to run across the water. Okay, it's what allows you to skip a rock. Okay, all of that stuff is because the water molecules on the surface can bond to each other, okay, and create that surface tension that allows the rock to bounce off. Okay. In fact, it's strong enough that if a plane comes in at just the right angle, the plane will bounce off. Okay, if you've ever seen that happen, the guy that landed the plane on the Hudson River there a few years ago, okay, he was kind of able to do that too. He kind of bounced the plane temporarily off of the water. Okay. Is that sort of making sense, this hydrogen bonding thing? Okay, so polar molecule simply means, okay, that we don't share the electrons equally. All right, so the sharing's not equal. Okay, some elements are more electronegative. We talked about that. Okay, oxygen is very electronegative, so it pulls the electrons down to its part of the atom more than they are up at the hydrogen part, and you can sort of see that in these diagrams here. Okay, there's polar bonding here, so we get positive charges near the top, negative charges near the bottom, and that means that one water molecule can bond to another, okay, through hydrogen bonding. Okay, and water molecules can bond to other things through hydrogen bonding as well. What happens to water when you freeze it? It expands. Okay? Does that happen with most things? Most things, when they turn from a liquid to a solid, shrink. Okay? Most things take up less space when they become a solid. Right? Water's another. Essentially, if there's a rule in chemistry, water's the exception to it. Okay? It's odd we ever made any rules in chemistry given how common water is. Okay? But water kind of breaks the rules. The reason that ice takes up more space than its liquid counterpart does is because, again, of these hydrogen bonds. When you start forcing this molecule and this molecule together, okay, sure, they like each other. This is positive, this is negative, but as this one gets close enough to this atom, okay, it starts getting closer to the negative part of it as well. And what will two like charges do to each other? They'll repel each other, right? It's like trying to put two north ends of a magnet together, right? They push away, and you can't do it. Well, it's the same with two negative charges. You can't push them together. They'll start to repel. So there's an attraction for a certain distance, and then once they get to a certain point, repulsion starts to play again. That happens at about 4 degrees Celsius. Okay? Water is at its kind of most dense at 4 degrees. Okay, and then right after that, it starts to push away again. And as the freezing process occurs, it pushes away, and you get ice that floats on top of water. All right, it is one of the few compounds whose solid floats on its liquid. Okay? If you take liquid mercury, okay, and then you take a bit of it and you freeze it so it turns to a solid, and you drop it in, it'll sink. Okay, you can't have a mercury cube floating in liquid mercury. It just won't happen. It'll sink to the bottom, as will most things when they turn to a solid. They end up being more dense than their liquid counterpart. Water, again, because it's a polar molecule, is the exception that proves the rule. Okay, it'd be pretty weird if lakes froze from the bottom, wouldn't you say? Okay, there'd be no hockey. Okay, if lakes froze from the bottom, there'd be no hockey. All right, because there'd always be liquid water on the top. Yeah. All right. So the water molecule ends up getting shaped kind of like a right angle because these two hydrogen atoms are both positively charged and they repel each other. So they have to stay a certain distance apart. It ends up being pretty close to 90 degrees. All right, so there's about a 90-degree angle between the two hydrogen atoms because of this repulsion that goes on between them. Okay, but again, you can see here that one water molecule can hydrogen bond to 4 others. All right, and that allows a fair amount of surface tension to happen. Okay, between water molecules and other water molecules. Okay, so that's kind of how that happens there. Okay, this is showing you what happens with the ice in the liquid water. So here's your liquid water. Okay, about 4 degrees Celsius or so, and you can see that the water molecules are, they're not tightly packed, but they're close. They can still change places, which is why you can pour it. Okay, but when it turns into ice, that repulsion happens, and you get this rigid crystalline structure forming. Okay, that is ice. Okay, is it always exactly the same? Are ice crystals always exactly the same? No, no two snowflakes are alike. All right, and that's because the way that the water molecules are arranged, okay, whatever way they're oriented, is always slightly different. So you never get two crystals to look the same. Okay. Now, I was saying to you earlier that these hydrogen bonds can happen not just between water molecules, but between water molecules and other polar molecules. Okay, ammonia, NH3, is an example of another polar molecule. Okay, and it has a negative end and it's got positive ends down here. And so water can hydrogen bond to it as well. Okay, in fact, we use that property for glass cleaners. Okay, if you've ever used Windex, Windex is a solution of ammonia and water. Okay. All right. Okay, so the big thing here, those strange properties of water, okay, have to do with the fact that it is polar. Okay, there's charged ends, okay, that attract each other and form those hydrogen bonds. Questions on that? Yes. Now, a lot of organisms on Earth depend on the fact that water is a polar molecule. Okay? Plants would not be able to transport water from their roots to the top of their leaves without it. All right? Because plants don't have a pump. Okay? There's no pump in a plant that pumps water from the roots to the top. Okay? A lot of people seem to think there is, but there isn't. Okay? They don't have a heart or anything like that that's actively squeezing, okay, water through the tubes that go to the top of the plant. They rely entirely on osmosis, which we'll learn about in the next unit, and the fact that water can bond to itself and other polar molecules. All right? So what happens is this. We get this process called cohesion. Okay? Cohesion happens, okay, when two water molecules bond together. Hydrogen bond together. It has to be two water molecules in this case. Okay? Cohesion, because they're the same. Right? So inside the tiny little tubes of a plant, okay, called the xylem tubes, okay, water molecules will hydrogen bond to each other. They will also hydrogen bond to the inside of the tubes. All right, so you essentially get this linking of the water molecules all the way up the tree. As water evaporates from the leaves, it's still attached to the other water molecules below it. So as it evaporates and leaves the tree, it creates a pulling force on the water molecules below it. And that is what draws it up the tree. Anyone ever played with like the barrel of monkeys when they were a kid? Right? The monkeys with the hooked arms? That's what it's like inside of a tree. Okay? The water molecules are like the monkeys in the barrel. Okay? And they hook their arms together, and you can pull up big strings of them by pulling on just the top one. All right? The others are hooked together, and they pull on each other. All right? So you get this barrel of monkeys effect from this hydrogen bonding that occurs. Now, it's not just that the water molecules are bonded to each other, because if they were, you'd have this length of water, this column of water that you would have to support. Okay? The water also bonds to the inside of the tree. All right? So it's like you got the barrel of monkeys, but you got some tape on a few of them that you stuck to the wall. All right? So now you don't have to support the entire barrel of monkeys, just some of them, and the wall supports some of them, okay, and so on. You guys get me on that? Okay, so it kind of works in that way, all right? And so it's really important, okay, in terms of being able to transport water. So we have hydrogen bonds between water molecules are this process, cohesion, okay? Hydrogen bonds between water molecules and other materials is called adhesion. Okay, so when you've got the droplet of water on the side of the cold glass, okay, that's adhesion. It's adhered to the side of the glass. All right. The other name for glue is often called an adhesive, and adhesive sticks unlike things together. All right, so adhesion is the process of sticking any two unlike things together. All right, so adhesion and cohesion, okay, working together are responsible for what you see here. Okay, this is adhesion. Okay, the beating up of the water on the leaf of the plant, okay, or the beating of the water on the surface of a freshly waxed car, or on the surface of a freshly painted deck, or something like that. Okay, this surface tension here, and shown in the glass, okay, that's cohesion. That's water molecules bonded to other water molecules, creating that meniscus, right? That apparently can support a paperclip. I've never been able to pull that off. Okay? I once spent like 4 hours trying to do that, and I decided it was 4 hours of my life I was never going to get back. Okay, apparently you can do that. Okay. All right, and then a couple of other examples. Obviously, you got the Jesus lizard here that can run across the small bodies of water, not terribly big ones. Okay, if you got your water striders as well, you've probably seen those, on a pond or a slough or something like that around here. Okay, those bugs that just kind of spread out like that. Okay, they can use they can stand on the surface tension of the water. Okay, simply because those hydrogen bonds are strong enough to support them. All right, you or I, no. All right. If we try and do that with just our hands and feet, we'll fall in, obviously. Okay? Can we still float on the water? Okay, but does that have anything to do with surface tension? No, it has to do with buoyancy, and that's different. Okay. All right, so that's what there is to know, okay, about solubility, terminology, and the polar nature of water. Okay, that'll kind of come up again and again here in this unit and a bit in the next unit as well. All right, you've got 20 more minutes. Okay, to get together with your group here and get all that pre-lab stuff done. Whatever you don't get done in class today, you got to get done for homework tonight, all right, so that you can go into the lab first thing tomorrow.